This is section 115. We're still in the Cartesian coordinate plane, and we're going to examine how points on the Cartesian plane are symmetric and how they can reflect over the plane. So one of the most important concepts in math is symmetry. There are many different types of symmetry, but we're going to discuss 3 for the Cartesian plane. Now there are more, and as we kind of unravel what's going on in this class, we're going to go over those other types of symmetry, but for now we're just going to focus on 3. So here's a definition. Gold flashcard: if we have 2 points, A, B, and C, D, they're said to be symmetric about the x-axis if A equals C, so the x values stay the same thing, but the y value went from positive to negative. They're symmetric about the y-axis if the x values went from positive to negative, but the y value stayed the same. And it's symmetric about this new term, it's symmetric about the origin if both the x and the y value change from positive to negative. Now, the best way to think about it, it's not necessarily just from positive to negative, it's the fact that there is an extra negative added into it. Because if it was negative and you added that extra negative, then it goes positive. So I know this is new, it's a little different. Let's kind of visualize it a little bit. So we have our definition up here. And so let's look at these different points that I would have up here. So we're going to have our baseline being point P. So we're going to say that point P and S are symmetric about the x-axis. So there's this symmetry where the distance from here to here, that distance equals each other. That's kind of like what creates that level of symmetry, if that distance is the same. Now, if you notice, the y value went from positive to negative, right? There was that extra negative added to the y value. And so that's why the y value had that extra negative added to it. And then we would say that it's symmetric about the y-axis, and that's going to be, so P and Q are symmetric about the y-axis, and here, it's this distance here that's the same. So the distance amongst those x values are the same, and it has that reflection, and it went from positive to negative, or thinking of it as that extra negative being added. And then point P, the point P here, we would say in relation to R, and then the idea is that it's symmetric about the origin because it has both a negative added to the x and a negative added to the y. Now Q or S, these are symmetric about the origin to each other, and P and R are symmetric about the origin to each other. So let's kind of practice that. What does this mean practically? So using the definition, how do I actually reflect things, right? Like that's where we're really trying to get at. So if I have point P and it's the point negative 2, 3, find the points which are symmetric about P. So symmetric about the axis. So that means that it has to be symmetric about this line here. It's the y value that gets a negative to it. So if my point is negative 2, 3, that means if I add a negative to my y value, I get negative 2, negative 3. So negative 2, negative 3. And then if I wanted to find the symmetry about the y-axis, I'm going to be adding a negative to the x value. So if I add a negative to the x value, negative 2 with a negative added there gives me positive 2. So then we have 2, 3 there. And then the origin, you add a negative to both. So negative to the negative 2, which is positive 2, and then a negative to the positive 3, which is negative 3. And so then that point, we're going to have, these are the points that create that symmetry. So to kind of summarize it, to make it a little easier, To reflect a point about the x-axis, replace the y with negative y. The y-axis, replace x with negative x. And then the origin, replace x with a negative x and replace the y with a negative y. You're doing both. So example number 2, plot the following point, 3, 5. So 3, 1, 2, 3, 1, 2, 3, 4, 5. So state the point that state the quadrant that the point is in. So that's going to be quadrant number 1. And then state what the point would be if reflected about the x, y, and the origin. So if I wanted to find the reflection about the x-axis, remember that means that you have to switch your y with a negative y. So if my y value is 5, switching it with a negative, I'm going to get 3, negative 5. And so that would actually be here, because this distance has to be the same as this distance. If I wanted to find about the x or the y-axis, that means I have to replace the x with a negative x. So replacing the 3 with a negative 3, I get negative 3, 5. And so negative 3, 5. This distance has to be the same as that distance. That's what creates that symmetry. And then the origin's probably always the easiest. You have to replace the x with negative x, and you have to replace the y with negative y. You're basically doing it with both. So you get negative 3, negative 5. So negative 3, negative 5. That's visually the point that's symmetric about the origin. If it helps you to graph it, go ahead and graph it. So what did we learn today? We talked about symmetry and reflecting a point over the x, the y, and the origin. The x-axis, the y-axis, and the origin. What is a visual to help you remember the symmetry? It's always helpful to draw it out. And so reflecting over the x-axis means that my y goes from positive to negative, or from negative to positive. If we're reflecting about the y-axis, that means the x goes from positive to negative, or from negative to positive, because that's where it crosses, or it moves into those quadrants. And then the origin is easy, it's just both. And then to reflect over the origin, what do I replace x and y with? We just said it. If I have the point x, y, you replace both the x and the y with the negative. This does conclude our lesson. If you have any other questions, please leave them in the comments.